Hello. We're going to look at the chapter Equilibrium, both chemical and ionic together, from the point of view of the JEE Main and the Advanced Exam. Let's start with the Advanced Exam. But before we do that, it's a very peculiar chapter, right? Because this is, the ionic part of it is tested more in the Advanced Exam. The chemical equilibrium part is usually clubbed with thermodynamics, sometimes ionic part also. When you look at the main exam, it's mainly just a combination of formulae that you need to know or some basics of how to set up equilibrium. We'll see what was asked in the last few years. So in the advanced exam, there were 2 questions asked in 2018. One had the ideas of thermodynamics and equilibrium. That was an MSQ, multiple select question. There was an integer question asked that was on solubility product as well as setting up the Ka value and all that, using the Ka value, solving it. No question asked 2017. 2016 had a paragraph question. 2 questions asked again. So a lot of weightage given in some years and some years is completely skipped. So in 2016, the 2 paragraph things. Now this was where you combined the degree of dissociation idea, equilibrium constant, as well as some thermodynamics ideas. 2015, 2 questions again. 1 MCQ, actually 3 questions. 1 MCQ that had the temperature dependence of equilibrium, and 2 more questions, which was paragraphs, so making a total of 3. These paragraph questions had ideas of buffer as well as thermodynamics. So usually what happens is that if it's an idea on ionic equilibrium or solubility product, it combines all the ideas that came before it, which is from regular equilibrium as well as thermodynamics. And chemical equilibrium itself, just by itself, is tested, almost not tested in the advanced exam. Look at the JEE Main, and specifically just looking at the 2019 paper specifically, we did that. Most of the questions were on, figuring out relationships between how to set up a basic equilibrium from scratch. Write down degree of dissociation, all of that, the expression of the equilibrium constant, Kp, Kc values, what happens when you add up equations, what happens to the add, subtract, multiply, what happens to the equilibrium constant there. Some very, very basic ideas tested. Couple of questions, just very few asked on pH. There are multiple formulae. So in the main exam, you're expected to remember those formulae. In the advanced, you can pretty much derive things. Anyway, so here some questions asked on solubility and pKa ideas. So let's get started with some theory now, and then we'll do some interesting questions. All right, let's get started with some theory on equilibrium. So here, generally till now, we've assumed that reactions go to completion. If you were to plot this on a graph, this is how it would look. You have R, some reactant giving some product P. So I'm plotting concentration versus time. Now this way, the concentration of the reactant reduces exponentially and that of a product increases exponentially. And after some time, reactant gets over, and some product is completely formed. That's what this green line shows, that reaction is complete. But in reality, this does not happen. Actually, there is something else that happens here. You see this graph here. This is what shows that, sure, the increase is exponential and decrease is also exponential, but increase of product and decrease of reactant. But after a point in time, both concentrations become kind of constant. This is what you actually see. And that's when scientists figure out the idea of equilibrium, right? So that there's a backward reaction also happening. Now, when the reactions become constant, when the reactant and the product concentrations become constant, after that point, you say that a reaction has achieved equilibrium. Although in this chapter, we're not really going to talk about time, but these graphs are really, really important. And sometimes the JEE Advanced Exam tests just this idea. Some really complicated things can be solved on this. All right. Anyway, so there's a forward reaction, backward reaction. Their rates are same as soon as equilibrium is reached. That's what you mean when you say that, hey, this is equilibrium. It's a dynamic process, which means that both forward and backward reactions are happening. All right. So this basically can be written as rates being equal will be negative of delta, that, the square brackets are activity or concentration in our case, minus delta R by delta T is equal to delta P by delta T, which is the product. If you have some sort of stoichiometric coefficients that are not 1, you just divide it by in both sides. So 1 by A times the reactants and 1 by B times the products. Negative sign shows that the concentration of reactants is decreasing as the concentration of products increases. The rate is always positive. Rate is this expression that you have here, delta concentration by delta time. So I know that why am I talking about rate? Rate is a kinetics idea. That's the thing. Everything from gaseous state on till electrochemistry are all of them, they're all related. So physical chemistry is quite easy that way so you need to start strong and the rest of it becomes easy. Let's look at the next idea here. So what does this rate look like on this graph that I showed you, the concentration time graph? This over here is simply dP by dt, the differential. And this here, when you draw a triangle, is going to be delta P by delta T. This I know is a kinetics idea, but still good to know right now. We'll do this in detail in kinetics again. Anyway, equilibrium is achieved in closed systems when temperature and pressure is constant. Very, very important idea. So K, next idea, the equilibrium constant is simply the product of all the products raised to a stoichiometric coefficients multiplied together, divided by the product of the reactants raised to a stoichiometric coefficient. That's what this symbol pi tells us. Pi is just like what you have, sigma is summation, so pi is just product. That's it. Anyway, so Kc, the equilibrium constant in terms of concentrations, is a function of the concentrations of the reactants with products, and Kp is a similar thing, which is a function of the partial pressure if you only have gases, or if you want to look at gases specifically, you want to study the gaseous part of any equation, any expression. So this P here, you can use ideal gas law again, gaseous state. You get N by V times RT. N by V is concentration. So there's a way to convert Kc and Kp, and this idea of ideal gas law will help you remember this expression easily. What is Kc and Kp? How they're related? Well, Kp is Kc RT part delta N. Sometimes students mug up the wrong equation. Don't mug it up. Remember this expression, just the ideal gas law, and from there you can almost kind of derive it. All right, quickly, just like a quick point for you to remember that you can, this is where delta N lies in this equation. All right, what is delta N? Delta N is basically the summation of the products minus the reactants, the number of moles, gaseous. All right, alpha, the next idea, is the degree of dissociation. And you need to figure this out by reaction stoichiometry. There's no way to do it. I'm just going to give you a simple expression, but this is just to tell you how things are done. Depending on the particular reaction that you're looking at in the question, you'll have to figure this out. So initially, if you have, say, some C moles, a reaction is A giving 2B. I've just chosen this. And at equilibrium, there's no B to start off with. Sometimes it's given to you that there's some amount of A, some amount of B. Nothing really changes. Yeah, here in this case I'm doing C into 1 minus alpha and C into 2 alpha. There you just have to change the arithmetic a little bit if you have some amount of product also start off with. Anyway, alpha is the degree of dissociation, and Kc can easily be figured out by using the definition of equilibrium constant, and this is the expression that you get over here. Now, if you want to convert this to Kp, or if you want to get Kp, you don't care about Kc. The starting point is the same. Yeah, what you need to do is get partial pressures. How do you get partial pressures? Partial pressure is total pressure into mole fraction. So get mole fraction. How do you get mole fraction? Get the total number of moles. I have the initial number. I have the moles of the particular substance at equilibrium. Divide that by the total number of moles. There you go. That's mole fraction. Multiply that total pressure. It's partial pressure. That's what I've done over here. Some things cancel out and rest of them remain. And yeah, then you get Kp to be the partial pressure of B squared by A partial pressure of A, assuming in this case B and A are both gases. So as I said, you need to figure this out using stoichiometry. I showed you a simple substitution, but depending on the particular numerical you have, you'll have to do this on your own. And this is the best way to do it. Don't try and mug expressions. Yeah, mugging is literally the worst thing you could do in this chapter, because there's just so much theory that it's really difficult to just try and mug it and then repeat it in an exam. Although in the JEE Main exam, funnily enough, this chapter is a lot more difficult than the advanced exam, because in JEE Main, you kind of have to mug some equations. Life becomes really simple if you know one equation and you just substitute it. I'll get to that. That's in ionic equilibrium. Anyway, let's continue our chemical equilibrium discussion. Q is the same expression as K, equilibrium constant. The only difference now is that I'm looking at concentrations at any point in time. Whether equilibrium is achieved or not does not matter. So that's the expression of Q. And why is Q necessary? Well, you look at a generic equation, right? General equation A times A plus B times B gives C times C plus C times D times D. And this expression, at equilibrium, Q value would be equal to the value of K. Now, if Q is less than the K value, the equilibrium constant, then the reaction moves forward to achieve equilibrium. And if Q is greater than equilibrium, it moves backward to achieve equilibrium. So this expression of Q will help you figure out which direction the reaction would move. And this is a very, very interesting thing. And this is tested a lot in the JEE Advanced exam and sometimes in the main exam as well. Okay, some ideas from thermodynamics that are important. We've done this in thermo also briefly. Let me do that again right now. At equilibrium, delta G must be equal to 0. What is delta G? Remember, gives free energy, that idea. So the expression for delta G was delta G is delta G naught plus RT ln K. Delta G naught will be equal to minus RT ln K at equilibrium because delta G is 0. Look at these graphs. This is the most important thing. It doesn't matter whether reaction is spontaneous or non-spontaneous. But the whole deal is that delta G should be 0, and this can happen from both sides irrespective of the reaction being spontaneous or non-spontaneous. See, that's what these graphs are showing us. repetition from thermo, I know this. G is minimum at equilibrium. All right, important idea to remember. A direct thing from here is that you get ln K2 by K1 is equal to delta H naught by R into 1 by T1 minus 1 by T2. This expression, you kind of have to remember. It'll make your life a lot easier if you know this. It is also derived from the previous thing. You assume that entropy has very little contribution to this, and you get this expression. So what this tells us is that if the reaction is exothermic, temperature increases, then K falls. Yeah, that's the direct implication of this. And this is tested a lot in the JEE main exam and also in the advanced exam at times. If the reaction is endothermic, temperature increases, increasing the K value. All right. Cool and really important idea right here. On to the Le Chatelier's principle, LCP, let's just call it that. So this, in layman's term, is when the equilibrium established is kind of disturbed, then the system tries to reattain equilibrium. The same thing you see everywhere, all across science, even in physics, Lenz's law is the same idea. You disturb equilibrium, it tries to come back to its normal place. Anyway, so if there's a change in pressure or concentration, the equilibrium shifts, and you need to calculate Q. If Q is not equal to K, then you figure out a direction in which the equilibrium moves in. That's it. So simple thing. Adding a reactant makes the reaction go forward. Adding a product makes the reaction go backward. Similarly, removing and adding, removing products and reactants, you can figure out directions. What's next is that the fact that the total pressure volume, that change affects the equilibrium only if delta N, the gaseous number of moles, products minus reactants, if that is equal to 0. If that's not equal to 0, only then equilibrium is expected, otherwise it's not. So assuming that delta N is not equal to 0, when you increase the pressure, the reaction moves in a direction to reduce that, which means it reduces the number of moles and the volume is constant. Remember it this way instead of trying to mug the infinite possibilities, permutation and combination. Not infinite, but don't mug that. It's better to remember this, logically. All right. The next idea is that if the volume increases, now for pressure to stay constant, this moves in a direction where number of moles increases. That's a simple idea. Now, inert gas addition, that has no effect at constant volume as the P partial pressure does not change. And you can figure out what happens at the other thing with constant pressure. There is an effect. You can calculate that by setting up a new equilibrium, figuring out Q, whether it's greater than or less than K, and get where the reaction will go to. That's it. Let's now move on to ionic equilibrium. A simple idea first, strong and weak electrolytes. Strong electrolytes where the K value is greater than 10 power 3. And you see these here, one acidic and one basic. Salt that dissociates completely. Strong acids and strong acids, strong bases, not salts. We'll get to salts later. Weak acids, weak bases where K value is less than 10 power minus 3. This is an approximation. So you have acetic acid as well as ammonia shown over here. But how do you know if something is acid or a base? There are many theories, right? So Arrhenius, Laurie, Bronsted, and also Lewis have theories, and we've given you a brief way of how to remember this. If H plus and OH minus ions are involved, that's the first one, Arrhenius, Bronsted, Laurie, Bronsted. This is the main one that we're going to deal with. That's H plus only. Either H plus is donated, acid, or accepted in case of a base. Electrons, donated and accepted. You can figure out which one's acid or a base. Now, the examples are given over here. Only case with electrons is that, look, BF3 and AlCl3 are electron deficient and they are acids. Ammonia and PCl3, they have extra electrons, they are bases. The rest of the things are pretty self-explanatory. Most important idea here, and trust me, I'm going slow here because this is literally the most important idea from this entire chapter, even more than pH, pK and all of that. This thing of conjugate acid-base pair. Okay, this is very useful in organic chemistry too. Whenever you do that, we'll look at it in detail again. So basically, things form an acid and base pair, conjugate acid-base pair, if they differ by an H plus ion. You see that over here, the pink line and the blue line over here, this denotes that. So H2S and HS minus, they differ by an H plus ion, and NH3 and NH4 plus, they also differ by an H plus ion, so they are conjugate acid-base pairs. The one that has an extra H plus ion, that's the acid. The one that is deficient is the base. Okay, simple idea. Try and remember it using this instead of any other way. They always come in pairs, conjugate acids and bases. Ostwald dilution law. Well, CH3COH, right? It's a weak acid, so it has a very low alpha value, which means that I can make this approximation when that 1 minus alpha is almost equal to 1 and alpha is equal to under root Ka by C. So this just means that as dilution increases, degree of dissociation kind of increases after a point. There's a graph that looks like that. Anyway, a simple idea, but really, really useful in solving really complicated numericals. Sometimes you can't make this approximation. You need to be careful. If the error is very high, is greater than 5%, then you cannot make this approximation. You get a quadratic equation that you have to solve. This is almost never tested, but sometimes an examiner might test that, so be careful about it. This may be relevant in the JEE Advanced exam more than the JEE Main exam. Yeah. All right, moving on. The conjugate acid-base pair, there and only there, remember, only there is Ka into Kb is going to be equal to Kw, the ionic product of water. So pKa plus pKb will be equal to pKw, which is 14. Ka and Kb are dissociation constants of the acid and the base specifically. And when I put a p before something, it's just saying it's negative log of that value. Okay, neutral pH is 7. Yeah, at specific temperature and pressure conditions, yeah, at 298 K and 1 atmosphere pressure. Now, dissociation of water specifically, this is interesting and it's been tested multiple times in the JEE Advanced exam. So pay attention to this. Dissociation of water is endothermic, which means that as T increases, Kw increases. So the neutral pH, that changes. It's no more at 7. It's going to be a lower value because pKw will reduce. Yeah, Kw increases, pKw decreases. All right, pH can be less than 0, can be greater than 14. Generally, you see 0 to 14. As pH increases, H plus ion concentration falls, OH minus ion concentration increases. Why? Well, because the multiple of both of them, H plus and 2H minus, is going to be equal to the Kw value, right? Okay, pH is a log and exponential scale. I know this simple stuff, but it's very important to revise this before you go into an exam. Common ion effect, the next and really important part. From this chapter specifically, I think this is the most important thing when you're looking at equilibrium in itself. But if you look at the whole of chemistry, as I said, the idea of conjugate acid-base pair, if one is weak, the other is strong. That's really important from organic chemistry. Anyway, common ion effect. Something, basically, if there's a common ion, this would suppress the formation of the entire species. So, if, for example, you use the idea of Le Chatelier's principle, you figure out Q and you get the direction which a reaction would move. Simple idea, but very, very useful in solubility, which we'll look at in some detail when we do the questions. Okay, buffer action. Yeah, this is usually something that students are kind of scared of usually, but it's not. It's again a lot of math. Let me just give you a cheat code here. Ionic equilibrium is a lot of math. Is simple algebra. You just have to take logs. That's what confuses students. So it requires a bit of practice, just like most of math does. In maths also, you can't remember equation inside out. Yeah, you have to wing a few things. Yeah, you have to be able to derive it on the spot. So that's what I would suggest. Although before an exam, it's better to know all equations, but it's also important to know all the steps that go into deriving them. All right. So buffer action is something that just resists pH change. Yeah, for a small range. So generally, weak acid and a salt of a conjugate base, that forms a buffer. pH value is given by this expression over here. Weak base plus salt of conjugate acid gives you a pOH value, which you can calculate here. Again, you can form this is for a monobasic acid or a base, obviously. Now, you can form this setup equilibrium and you get this by taking log on all sides. You see that salt by acid thing? This expression works if that ratio is not greater than 10 or not less than 1 by 10. Yeah, if it's beyond that, then the pH does change. All right, weak acid plus weak base always forms a buffer. Always and always. Figure it out because you get a salt and that hydrolyzes. Solubility, the last part and literally the most important part from the point of view of the JEE Advanced exam, because it combines everything from normal equilibrium, also ionic equilibrium, common ion effect, buffer, everything. Buffer is not so much, not tested at this level, but common ion effect definitely is. So KSP, the solubility product, is generally spoken of when you have a sparingly soluble salt, which means that I put it into water, it doesn't dissolve completely. Only some of it dissolves. Now, this is a function of solubility. Solubility is just a concentration at the saturation. Okay. You can figure this out by reaction stoichiometry. Please don't mug this. Please don't mug KSP values at, oh, this is a 4s cube or whatever. Just do it from the basics. The ionic product, which is just like Q, what you had at chemical equilibrium. If the ionic product is greater than KSP, then precipitation happens. If it's equal to KSP, then saturated solution. If it's less than that, then you can add a little bit more salt. That's what that means. Solubility can be suppressed. Yeah? Something may be a little bit soluble, but if I put a common ion there, kind of pushes the equilibrium backwards. This was the idea that I was telling you that's tested repeatedly in the advanced exam. And this is also useful in qualitative analysis. Yeah, that brings us to a close of the whole theory part. Let's start with some numericals. Okay, so this question can have more than one correct answer. Graphs, and like graphs. We're plotting the concentration of the reactant A versus time as well as the product versus time. A kind of falls and P increases. That's expected. Information that's given to us is that T2 is greater than T1 and ln K1 by ln K2, which is at the respective temperatures, greater than T2 by T1. This is interesting. Let's see what we can do. Looking at the options, it looks like we're going to have to figure out what delta G, delta S, delta H signs are. That's it. Once we do that, things should work out. All right. So this is the graph over here. Yeah, it's again in front of you. The colors just show the different times. So let's do this. So as T2 is greater than T1 from the graph, this is at equilibrium. What can you see? I think I can say right from here that A1 is less than A2. What is A1 and A2? The concentration of A at temperature 1 and temperature 2. You see that, right? The pink line is below the orange line. Yeah, that's what's marked over here. Now, what else do I have? I also have that P1 is greater than P2. What is P1 and P2? Yeah, look at that. The pink line over here is greater than this. What does this imply? This implies that, well, the reaction goes much further at T1 as compared to T2, which means that as temperature increases, K falls. Why? Because T2 is greater than T1, right? So this delta H of this reaction is less than 0. There we go. We found out one thing already. So what is this? Is an exothermic reaction. Let me just write that down. So this is an exothermic reaction. Yeah, 1/3 way there almost, right? We need to find a couple of more things. So now what's next? K, is already on your screen, is simply going to be equal to P by A. And as the graph flatlines, equilibrium is reached. This makes sense, right? What do we mean flatlines? The concentration stops changing. That's what equilibrium means. Okay, yeah, this kind of makes sense. So what can I do over here? Well, I know for sure, looking at the graph again, that as this value, all of A is below 5. Yeah, this is the 5 line. And all the A concentrations are less than 5 mole per liter. And what about P? Let's see. Yeah, P, these guys over here. So P are all greater than 5 mole per liter. It's concentration. I need to put those brackets. Don't forget that. So what gives? I think what we can do from here is that figure out the delta G value. Yeah. Here, delta G naught, not delta G. Delta G is 0. Yeah. At equilibrium, delta G is always going to be 0. So delta G naught is going to be equal to minus RT ln K. K is greater than 1. Why? Because I was comparing P and A, right? Now this is some number greater than 5, this some number less than 5. Right, so this number is going to be greater than 1. That's what I'm trying to say. That's it. Simple math there. So there you go. If K is greater than 1, and from this equation, delta G naught must be less than 0 here. So this delta G naught is less than 0. This is negative. There you go. So I figured out delta G naught is less than 0. I also have the sign of delta H naught. That's also less than 0. We're getting there. Okay. We have this next thing. We say that ln K1 by ln K2 is greater than T2 by T1. This will help us figure out the sign of the next thing, what we need, delta S naught, right? Let me write down what this is from this expression on top, from this guy here. So this is simply going to be delta G naught by RT1 divided by delta G naught by RT2, which is going to be greater than T2 by T1. So I think a lot of stuff will cancel out, right? Especially the temperatures. Yeah, sure. This is what you get after cancelling out the temperatures and substituting delta G naught going to be equal to, I'm just saying here that delta G naught is equal to delta H naught minus T delta S. That's what I've substituted over here. And I've cancelled out the temperatures here, because this is, all right, we're getting somewhere. So I finally got delta S naught in my expression. I know what delta H naught is. Delta H naught is less than 0. Okay. And T2 is greater than T1. I also have that. Now, what can I do here? So, okay, delta H naught is less than 0. Now, for this denominator has to be less than the numerator for this value to be greater than 1. Did that sound right? Yeah. All right. So, for this to happen, delta H naught plus T1 delta S naught must be lower than this guy over here at the bottom. Now, that's possible only and only if delta S naught is less than 0. Yeah, because T2 is greater than T1, which means that this term over here, T2 delta S naught is more negative than T1 delta S naught. That makes sense? Yes, it does. So denominator is less than numerator. Negative signs cancel out. So yeah, this thing here is correct as well. So delta S naught also is less than 0. There you go. I have all the 3 signs. And funnily enough, All of them are negative. So delta S naught is negative, delta H naught is negative, and delta G naught is also negative. Yeah, so I can figure out the answers that match from here and you can mark them. There you go. So I know this is kind of intensive, more of a derivation like thing, but hey, we use all the information given to us in the question. Yeah, although some of it was weird. We also looked at the graph. We were able to figure out the value of K just by graph. Using that, we got delta G naught. So that was the main thing there. After that, I think it was just more of mechanical stuff. And so the answers are marked on your screen. That was it. Okay, this question requires a numerical answer as an input. Let's see. We've been given ZnOH whole twice, yeah, zinc hydroxide. This gives us two expressions. Yeah, when you put it in water, it dissociates, gives you Zn2 plus and OH minus ions, but not entirely. Yeah, solubility equilibrium setup. So you need to use the KSP idea over here. Why would you do that? Well, the second one, the OH minus ions formed here react with more Zn2 plus and you get a complex. Yeah? So equilibrium is set up over here. You get the value of equilibrium constant Kc. That's given to us. What we need to do is find out the pH of this solution when the solubility is minimum. Interesting question. Let's get started. So let's write down the equilibrium expressions. The one place where you could mess up is assume that both of these equilibriums have the same concentration of, well, OH minus ions and Zn, the complex. Yeah, does that happen? I don't think so. Let's do this one step at a time. Okay, so at equilibrium, you have this ZnOH whole twice. This is the expression over here, the first one. This is the KSP idea. So at equilibrium, what's going to happen? This is solid. I'm going to ignore that. So let's say the solubility due to this is say S1, and this would be 2S1. Yeah, so KSP would simply be S1 times 2S1 whole square, which is 4S1 cube. Yeah, but you don't need all this. Why? Because you know the concentration of this. Yeah, you know that OH minus ion concentration is some value. But I'm concerned mainly with Zn2 plus over here because that is going to give me the solubility. Yeah, S1 is the solubility from this expression. So let's calculate that in terms of OH minus ions. I'll tell you why I'm doing that very quickly. So here I get S1 to be equal to KSP divided by the OH minus ion concentration whole squared. That's from this first setup. Now the next one, the OH minus ions that are formed over here. Let's see what happens. These react with ZnOH whole twice and give me this complex ion. Okay, so that's the thing. This reaction happens only because of the really tiny amount of OH minus ions formed over here. So I'm going to put that same thing here. I'm going to put 2S1 over here. This is solid, so I'm going to ignore this. Zinc, I'm just going to ignore this one. Here, what's going to be formed is S2, a new expression, right? A new solubility idea. Now, this S2 is the solubility of this. Now, how do I set up this equilibrium over here? It's just simply going to be S2 times S2 divided by 2S1 whole square, right? This makes sense? Yeah. This one's fine. So now, let's get an expression of Kc in terms of S2. I have that. So, okay. Oh, here again, this is simply 2S1 is the same as OH minus ion, right? So I'm going to put that here. So S2 now is going to be equal to Kc times OH minus ion concentration whole squared. Why did I do this? Now, here's the thing. The solubility, the total solubility, S is going to be equal to, well, the summation of two things and the S1 and S2 basically. And for minimum solubility, this expression ds by DOH minus should be equal to 0. That's the one trick you need to use. And also the fact that S1 and S2 are separate, they're not the same thing. So you can't just take the same solubility for both expressions, you'll get a completely different expression. So these two tricks you need to keep in mind, these two ideas. All right, so anyway, now S, you get an expression in terms of OH minus, right? Only then can I go and differentiate it. So let's do that. What was S1 and S2? I get, this was KSP divided by OH minus whole squared, that was S1, and S2 was Kc times OH minus whole squared. S is this expression. Now differentiating this and equating it to 0, what do you get? And this is simple differential, right? So I get a minus 2 on top because that was OH minus whole square, and this becomes OH minus the whole cubed. KSP, I'm going to put that on top. Yeah. And this here, there's a 2 there, this 2, right? So differentiate that, I get 2 Kc times just OH minus. This whole expression should be equal to 0. Oh, this doesn't look good. This looks weird. Let me write that properly. Okay, so this -2 is on top, just clarifying it's not at the bottom. All right, so this is what you get. Now, let's solve this. That's all we need to do. Once you solve this, we can get what the OH minus ion concentration would be and then get pH. That's why I did this. That was the whole point of differentiating with respect to OH minus, because once I get OH minus concentration, pH plus POH is equal to 14, I get pH. Yeah, that's why this makes sense. All right, so now where was that expression? Let me keep that here. Okay, so now I simplify things over here. I get KSP plus 2Kc times OH minus whole to the power 4 is equal to 0. Does this make sense? Yeah, sure. This one makes sense. So that means that the OH minus ion concentration whole to the power 4 would be equal to, there was a negative sign here, right? And this 2 kind of goes away because 2 was cancelled out from there too. Okay, so now this is going to be equal to what? It's going to be equal to KSP divided by KC. Yeah, now we're getting somewhere. So this was simply 1.3 into 10 power minus 17. I'm now substituting stuff. This is the last step. This is what I like doing, and I think you should do. Put the substitution should happen right at the end. Everything else is variables, just like math. That way you're not going to make any mistakes. Okay, now KC was what? Oh, this is coming to be quite neat. So OH minus whole power 4 is this expression. And from there I get, the OH minus ion is going to be equal to the concentration. This is going to be 10 power minus 16 whole power 1 by 4. Just divide this so you get this to be equal to 10 power minus 4. Okay, so now this is OH minus ion concentration. POH is going to be equal to 4. Therefore, pH is 14 minus 4, simple stuff, which is 10, which is your answer. So there you go. This is the whole numerical. Couple of important things. Just a quick summary of what we did. First thing, S1 is not equal to S2. They're different things. Because of S1, S2 establishes. See that over there. The OH minus ion concentration formed when zinc gives you ZnOH whole twice gives you zinc 2OH minus. That reacts with the pre-existing ZnOH whole twice and gives you this complex ion. So this S1 and S2 cannot be the same. They're different. That's a starting point. We figured out S1 and S2 in terms of OH minus and KSP and KC. Why did we do that? Because our end goal was to figure out pH. And once you get POH, you can get pH. How do we get POH or OH minus? Well, we had this condition that it should be the solubility needs to be minimum. What solubility? Total solubility S1 plus S2, which we figured out in terms of OH minus. Differentiate that, equate it to 0, right? Because that's what the minimum is going to be. And there you go. Answer is pH equals 10. Basic solution. Okay, here's a question where it can have more than one correct answer. This deals with solubility ideas. So AgCl is dissolved in water and a few other salts. You have to figure out. These options are a little confusing, right? You need to compare S1, S2, S3, S4. So what we're going to do is we're going to find each one of them individually. Okay, so we're going to find S1, S2, S3, S4, and then we're going to, kind of compare them. Let's do that, yeah? This is one of those questions where it's difficult to do other stuff. Let's see the trick to it at the end. Okay, so let's write down the first expression. This is AgCl, Ag plus and Cl minus. So there's some solubility this would have. This is, have the same solubility value. Remember, there's a double-headed arrow here because, this is sparingly soluble salt. So a KSP idea would be required here. So KSP would be equal to simply S1 whole squared. And there you go. S1 is going to be the root of KSP. This is a simple idea. So this would be under root of 1.8. I'm not going to calculate this. Yeah, there's some value. Doesn't matter so much. Let's leave it like this. Let's see later what we want to do with it. Okay. So this was the solubility of just AgCl in water, nothing else. Now if I add another salt to it, what happens? Let's see. So I've put AgCl now in 0.01 molar CaCl2. Now this KSP is going to be equal to S2 times Cl minus. Why? Because the Cl minus that comes from CaCl2 is a common ion. All right. And because this is a salt that is not sparingly soluble, it completely dissociates completely, and yeah, all of it is available to fit into this equilibrium. And how much of it do I get? Let's see. So I have 0.01 of this to start off with. Yeah, in the beginning, like let's start So once dissociation happens, this gets used up completely, and I have 0.01 of this and twice of that. Yeah, this is one small place where you could mess up, and hence the answers could be very different. So be careful about this stoichiometry. So there's twice of this over here. Now in this case, let me just scroll down. Okay, give me some space. There you go. So KSP now is going to be equal to this value S2 times 0.02. I hope this idea is clear. Yeah, the common ion effect kind of should suppress the solubility, right? That's what you've learned. That's the theory. Let's see if that actually works out. So S2 here now is going to be equal to KSP. What was that? It was 1.8 and 10 power minus 10 divided by 0.02. So this is equal to 9 into 10 power minus 9. Exponentially smaller, right? That was the order of 10 power minus 5 or something. So this is S2. As expected, it's lower, much lower because of the common ion effect. And that's what happens throughout this numerical. Yeah, the common ion effect suppresses all the concentrations, but to what effects we'll have to see. But clearly, S1 must be the highest. Yeah, that's for sure right now. And that's one trick you should keep in mind. And that's one thing you should realize right away, because all the other common ions suppress this. Okay, anyway, let's look at the next one. I have AgCl dissolved in 0.01 molar NaCl. KSP is similar. Now I've written this S3 times Cl minus. Again, NaCl is a salt that dissolves quite well. How much do I have? I have 0.1, same amount, 0.01 to start off with. So at just start in, and then once it dissociates, as soon as I put it in water, gives me 0.01 here and 0.01 here. All this is concentration, moles in 1 liter, so that's molarity. It couldn't be the same as molarity. So KSP now, as I said, is S3 times 0.01. Simple calculation. Yeah, so S3 is going to be equal to 1.8 into 10 power minus 10. And I've actually remembered the value, the number of times I've done this, right? So, okay, so 1.10 power minus 10. Divide this by 0.01, and what do you get? You get 1.8 into 10 power minus 8 molar. Interesting, right? Now, this one is slightly higher than the other one because there the concentration of Cl minus was higher. Just by looking at that, we don't actually have to calculate this. That's the trick. Just by looking at these numbers, you will be able to compare between S2 and S3. Hey, you know what? S3 is going to be higher. Why? Because, well, chloride ion concentration is lower, which means the suppression is going to be lower here. That's the trick that I was talking about. Anyway, since we are almost all the way there, we just have like one to do. Let's continue this. Let's continue solving it the way we are doing it right now. Last one, right? I have AgCl in 0.05 molar AgNO3, right? Now, KSP here is going to be Ag plus times S4. Why is that? Well, here, the common ion changes, yeah? It's Ag plus now. It's not Cl minus anymore. I know it's a very trivial thing, but it's important to recognize this. Yeah, so S4 now would be the one that corresponds to the solubility of chloride ion, and hence the whole salt, AgCl, right? So that depends on the chloride ion. The rest of it is similar, yeah. I have AgNO3 giving Ag and NO3 minus. So, yeah, initially was 0.05. That again, I'm starting. And as soon as it's put into water, this gives me 0.05 moles of this and 0.05 of this. So now KSP, let's scroll down, give me some space. So KSP is going to be equal to 0.05 times S4. Simple calculation. S4 would be the same value, 1.8 and 10 power minus 10 divided by 0.05, and yeah, that value is even lower, right? It's 3.6 into 10 power minus 9 molar. Okay, so what did I get from here? S1 was definitely the highest. Yeah, S1 was the largest. Highest is the wrong word. Largest. Then you get S3. Then you get S2. Then you get S4. This is all I need. Yeah, then I can figure out which one fits. So S1 greater than S2. Yeah, sure, this one's correct. What about S2 greater than S3? Nope, this one's wrong. This one's not correct. What about S3 greater than S4? Yeah, sure, this one's good. S4 greater than S1. This one's wrong. So your correct answers are options A and C. This is a simple way to do it. And as I said, the trick would be to realize that AgCl and water would have the highest solubility. So that's option A is definitely correct. Yeah. And then on comparing options B and C, you would realize that AgCl NaCl, AgCl NaCl and AgCl CaCl2. So and the concentration is the same. So CaCl2 would have a lower solubility value. You can figure that out without doing the calculation. And the last one, it's much higher than the other two. There's no comparison. Yeah, the concentration of AgNO3 that you put in. Therefore, the solubility will be suppressed even more, and that would have the lowest value. That's the trick. That's the way to do it really quickly without actually even solving this. But here you go. These are the answers, options A and C. Okay, this question requires us to give a numerical answer. Let's look at it. So copper 1 forms a complex that's given to you over here, and along with Cn minus. The equation also is here. What happens is we put NaCN, 1 molar of it, 1 liter of it, and there's a lot of CuBr around. So yeah, some sort of equilibrium forms, and we are asked to find out the concentration of Cn minus ion at equilibrium. Now, my analysis of this, what's happening here? I think what happens first is CuBr reacts with NaCN completely. Yeah. Does that make sense? It reacts completely, uses up all of the NaCN and then forms an equilibrium backwards. Is that true? There's nothing about CuBr and NaCN reacting, right? I know for sure that CuBr forms an equilibrium expression. That's on your screen. Cu plus Br minus, that's a sparingly soluble salt. So small value, Ksp is 10 power minus 5. And the other one, that's almost complete, right? It's all 10 power 11 is the K value, Kf here. So that's why it's written as Kf. This is an expression. When I sum them both up, then I get the expression CuBr plus 3Cn minus, giving me this. What's the K value of this? I said that this reaction goes to completion, which means that K value should be really high. Yeah, sure. Just by looking at these numbers, we can figure this out. Let me just scroll down a bit. I think this reaction goes to completion because K is going to be much greater than 10 power 3. Just to prove that to you, let me write that down. K equals Ksp times Kf, which is going to be 1 into 10 power 6. Yeah, definitely greater than this. So this one works. So what happens here is that this CuBr reacts with 3Cn minus. Let's form this equilibrium expression. Although it's not really equilibrium because it goes to completion. But anyway, so I have, say, initially 1 mole of this, right? Because it's a NaCN gives me Na plus 1 mole and Cn minus 1 mole. Although it's 3Cn minus, don't put 3 here. Yeah, it's not going to happen. NaCN is not going to form 3 moles of Cn minus ions. I know this is a silly thing to say, but students end up making such mistakes. So what's given to you in the question, just put that there directly. Don't think too much. Okay, initially, all right, I have 1 and none of these at equilibrium. Let me scroll down here. I don't have space, right? Let me scroll down a little bit. Okay, here. So at equilibrium, what happens? I have 1 minus 3x if x each of these are formed. Yeah, simple stoichiometry. So this is testing all your chemical equilibrium ideas, everything together. Okay, and x of this are formed. All right, going further down. Now this reaction goes to completion. That was your biggest hint. What does that mean? If this reaction goes to completion, and remember the Kf is really high, that means that 1 minus 3x should be equal to 0. All of it should get used up. There's no equilibrium, right? This is actually just completion. So it's not really equilibrium. From here, I can get the x value to be equal to approximately 0.33. That makes sense. This is the molarity here. Why am I doing this? Because the next step is the most important step, and that's what the examiner is testing, right? The next step is that this reaction now, I told you already this most important step, is that now an equilibrium is formed. Once it gets formed completely, this reaction goes back ever so slightly. It goes forward a lot, goes back really, really slightly. That's what these weird arrows mean. All right, so now the new initial value, so to speak, is going to be 0.33 and 0.33. And at equilibrium, there's none of this initially. At equilibrium, what happens? I'm going to use a different variable here. Say y of this gets used up. Same amount of this is going to get used up, Br minus, right? 3y gets formed. Be careful here. Don't write y. It's 3y. Look at the stoichiometry. Okay. Now all we need to do is write down the beautiful K expression, which is simply this 0.33 minus y whole squared divided by 3y should be equal to the equilibrium constant over here, which we calculated. We did that is equal to 10 power 6. I think y is going to be really, really tiny. I think y is going to be really small. So I can remove it from here. Yeah, this is almost going to be equal to 0.33 whole squared itself. So I'm going to remove that from here. I think that's an approximation I can afford to make. So what I get is this expression is going to be equal to 0.33 squared by 3. Oh, wait, hold on. I made a small error here, didn't I? This is 3y, sure, but this should be 3y cubed. Yeah. Be careful. I made an error. So could you? This is 3y cubed. Okay. So divided by, say, 27y cube is what I have here. And would be equal to 1 into 10 power 6. So I'm getting an expression which is cubed. So let me play around with math. From here on, it's just simple math. Yeah. I get a value of y. 3y should be my answer. So I can actually just solve for 3y if I'm smart. But let's do it with the hammer way. Let's get y in. Then multiply it with 3. So you get, well, y is obviously much smaller than 0.33. That's why I made the approximation. Remember, this is really important. All right, so y is going to be equal to cube root of 0.11 divided by 300, which is equal to 1.6 into 10 power minus 3. The examiner has given you weird things. We're like, why do you have the cube root of 110 and 120 given to you? So that this substitution is easy for you. We don't want to test your cube root finding skills. We just want you to do the actual numerical. That's why that was given to you. All right, so the answer, which is 3y, is equal to 4.8 into 10 power minus 3 molar. Quick tricks. The first one obviously is just find 3y directly. You don't have to find out y. That's the first quick trick. Summary of everything we did. This is the answer. This is definitely the answer. The summary of what we did to start with. We've used the basics of equilibrium constant. We set up an equilibrium. We saw two equations. We did not know the equilibrium constant of the third one, but we knew for sure that reaction is happening because that's what's given to you. You have COBr reacting with NaCN, which is basically CN minus ions. Make sure you write you balance this reaction, otherwise the entire numerical would be completely messed up. Once we did that, we said that, okay, this reaction goes to completion, 10 power 6, very, very high K value. Then it forms an equilibrium backwards, which is why you get CN. You may be tempted to write, hey, you know what, CN minus should be 0 because that's 10 power 6, but that's not true. That's the whole point that we've been trying to drill into your head when we're doing equilibrium. Every reaction goes a little bit forward, a little bit backward. So it's a tiny value, just 4.8 10 power minus 3, but it exists. So this is your answer and not 0. Don't be tempted to just mark that. There's no shortcut here. There are tricks that you need to spot to be able to solve this, but there is an answer. It's a finite value, which we just found out. And your answer is 4.8 into 10 power minus 3 molar. Okay, this question expects a numerical answer. And we have a sparingly soluble salt given to us, AB. What happens here is that at pH 3, it has some solubility. We are asked to figure out what that solubility is. Now, this is a weak acid. So something interesting happens, right? That means it would form an equilibrium with, if HB is acid, it would form an equilibrium giving you H plus and B minus. So practically, if I put HB in water, it forms a, expression that because of the solubility, a KSP thing, and HB, so B minus hydrolyzes and gives you back some acid. So that's why this seems a little complicated, and the solubility would be slightly different than what you expect it to be. So let's see. Let's figure out what this solubility should be like. So firstly, it's a weak acid and sparingly soluble, and the saturated solution hydrolyzes. These are two ideas we'll use. If S is solubility, X can be the amount that hydrolyzes. Let's do that one by one. Okay, so this is at saturation. What happens if I have some S and say S minus X of B minus Y, because B minus hydrolyzes just a little bit. Okay, S minus X would be, actually no, it hydrolyzes quite a lot. S minus X should be really small. That's what I'm guessing right now. Right? I'll tell you why. Let's see. Let's see if my guess is right. So KSP now will simply be equal to S into S minus X, which is going to be equal to 2 into 10 power minus 10. This value is given to me in the question. Now this B minus at equilibrium forms this expression. That's what I was saying. This is the same as hydrolysis. Yeah, this is since it's an acid, that's why it's H plus and not water in itself. So here, this B minus is going to be, what was that? It was going to be S minus X, right? That's what we got from the old thing. Now here, the pH is going to be equal to 3, which means this is 10 power minus 3. And HB is what is formed, which is because of this hydrolysis idea. So now, for this expression, what we're going to do is, let's use the Ka idea over here, okay? For this reverse reaction, which is the actual... So see here, why did I say reverse reaction? This expression over here, this is not that would give you the Ka expression. Yeah, Ka is going to be, well, the product of the ions, the plus ion, the negative ion, divided by the acid, right? But this is the exact opposite of that. So that's why I'm saying we reverse it and we get the regular expression. Or if you want, you could, invert the value of K. That works fine as well. Because if you reverse the reaction, the K value gets inverted. Yeah, if it's K, it becomes 1 by K. A simple idea from chemical equilibrium. All right. So now at equilibrium, what happens? Yeah, let me just write that down again. So X 10 power minus 3 and B minus was S minus X. So Ka is going to be simply 10 power minus 3 times S minus X divided by X. Okay, simple math over here. Now from here, I can get by, manipulating this and that. You get s minus x by x to be equal to 10 power minus 5 because I have the Ka value. So this is an important equation. I'm just going to mark it as 1. So I use this and the previous idea from KSP. I get that s into s minus x would be equal to the KSP value, which is 2 into 10 power minus 10. Okay, so I have two equations. This is the second equation and two variables, s and x. I'm doing the right thing when I equate the number of variables to the number of equations. That's an important point to check. Okay, now all I have to do is divide the second by 1, and what I have left is, let me write that down, 2 by 1, because remember, we figured out the number of equation variables the same. So if I divide 2 by 1, I'm going to be able to solve for s, which is my main goal over here. So sx was equal to 2 into 10 power minus 5. That's what I get when I divide 2 by 1. Let me write this down as 3. So I know what sx is, and I also know that s square minus sx, which is the second equation, is 2 into 10 power minus 10. So all I need to do is plug this here. I put this here. Because this value is really tiny in comparison to, this expression 3 over here, I can kind of ignore it altogether. So s square is almost going to be equal to sx, which is this value right here, 2 into 10 power minus 5. This is an important step, an important approximation that you should make here to be able to figure out the s value right away. From here on, just substitute. So if s square is almost equal to, let me write that again, empty space, and 10 power minus 5. So you get that s is going to be root 20 times 10 power minus 3, right? I'm just putting 10 inside it so that our root thing is easier. This is 2 into root 5, which is 2.236 times 10 power minus 3, approximately equal to 4.47, which is my answer right here. So a couple of steps. Most important thing to realize is that two things happen here. First is the solubility, sparingly soluble salt is put into water, so it forms an equilibrium. You can figure out its value by KSP. Usually, this is the idea of a salt, but this is an acid, right? So the hydrolysis idea also comes into the picture. Usually you react it with water and you get something, but here, in this case, since it's an acidic medium, that's why I put only H plus over there. It's the same idea. And once we set up that expression, we figure out how much of the HB is formed, and using the Ka value, we formed a couple of equations, two variables, and we very slightly divided them to get rid of some things, and we got the value of Sx, and we had S square minus Sx. So then you substituted it there, and then it was simple math. So this is a repeating trend in ionic equilibrium. A lot of math, a lot of algebra, ability to convert between the exponential log scale into the regular equations that you would have. So that's what you need practice with. This is a JEE question, and answer is 4.47.
For more videos and live lectures on the JEE, click on the subscribe button now.